Okay, so let's get started. So in this video, we will learn one of two methods that we can actually use to do model-free predictions, so to estimate a value function. In this video, we will talk about Monte Carlo policy evaluation. So where are we right now? So maybe you remember our small outline for the first few videos. So we started with an MDP and we extracted an optimal controller through means of dynamic programming. And now we consider the case where we don't have actually a model of the environment. And we instead want to estimate our value function based a given policy pi. Okay, so what do we assume now? So we assume that we know that the model of the world can be described by an MDP. So the thing is, we still assume that there is a Markovian representation of the states, and there is an MDP that actually describes it, meaning that we know the discrete state and action spaces, i.e. we know S and A, and we can interact with the world through some policy pi, might it be random or some well-informed policy, and we might receive experience samples from the environment. So actually we get actions. So if we perform actions in the environment, you remember the agent environment interface, you receive samples of the form S, A, R, and next state. So state, action, we get a reward, and we get the next states. So what this actually means is we do not know P and R, but we do know that there is an MDP that describes P and R, and we know how states and actions look like. So this is some well-known or some well-assumed, well-based assumption that we can actually assume in practice. So the general idea now is that we actually sample the environment in order to estimate the true state value function or state action value function for a given policy pi. So we want to actually estimate V pi of S or Q pi SA, and we can then use and these value functions are actually an approximation of the true value functions. In this video we will cover Monte Carlo learning, and in the next video we will cover time difference learning. Remember, as I also taught in the last video, like in the beginning, we solved the game of grid world, for instance, in dynamic programming while not actually playing the game, which is different now. So now we're actually playing the game in order to estimate the value function. So we actually play the game through states and actions, and we get the samples through the environment, and we have no knowledge of the real transitions or the reward function, but we implicitly sample the environment, and then we receive implicit information about the underlying dynamics and P and R. Okay, so maybe let's go ahead. So let's start with Monte Carlo learning. So let's maybe start with an example. What's the intuition behind Monte Carlo policy evaluation? Assume that we again have the grid world that we also discussed in the dynamic programming lecture, last lecture, and assume that we have some randomly given policy that's just saying something like this. So if I see this state, the policy will return action up. If I'm in this state, the policy would return action right. So just imagine that we have no idea about about our grid world or any dynamics or any reward function. We just see this one. And the question is, how can we now learn a value function without actually knowing the transition dynamics? And the idea of Monte Carlo learning is simple. It just says we randomly select a state where we actually start, and we just follow our policy. And if we do this, we get a bunch of trajectories through the environment. So in this example, we start here, go all the way up and right. So we selected actions, and this is actually where the actions take us. So in this case, you remember in the first lecture, you might select up, or you might select right, and it actually takes us up. So this is something that we actually receive. So we select actions given our policy pi, and these actions take us to some states. The environment returns these states to us, and this gives us a state action reward sequence, and the episode at some point will terminate. So in this case, you actually see 4 full trajectories, one starting in here, going all the way up and right until the terminal states, one starting here and going to the right until the terminal state, and these two going along these ways. And the question now is, you now got experience from the environment. We actually did not see this something for this state, but we get information about the environment, and the question is now, how can we use these information or experience samples to actually build knowledge about our value function? And the idea behind Monte Carlo learning is simple. We just calculate for each of the trajectories we have seen. We calculate the average return for this state, so we can, for each state on each action, for each state visitation in each trajectory, define what was the return that I got following my policy from this state onwards. And this is something we can just compute from this trajectory sequence. And if we compute this per trajectory, and for each of these states we maintain the statistics, we can actually average all the values for each of the states we encountered, and this is our current estimate of the value function. So given these 4 trajectories, a simple averaging, so a simple calculating of returns, I think it's a discount factor of 0.9 in here, would just eventually lead us to this estimation of our value function. And if you look carefully, and if you look at the values, they already seem to be very reasonable at this point. So also, if you remember what we did in the dynamic programming lecture, where we actually talked about value iteration. So what you see here is the current representation of the state value function by calculating it over value iteration after 10 iterations. And although the values are not equal at this point, because value iteration also took 10 iterations and it requires a lot more computation so far, our values really begin already to get close to this. So this is maybe the basic idea. Without knowing the environment dynamics, by just experiencing the sample trajectories, we can just estimate the value function. And this brings us actually to the Monte Carlo policy evaluation, which is the basic algorithm that we will cover here. So formally defined, what we also through an intuitive discussion, what we discussed in the previous slide, in Monte Carlo methods, we try to learn a value function from episodes of experience that we gain under policy pi. This is something that you will also often see. So we actually sample a state action reward sequence from policy pi. This is an expression that you always see something. We sample the sequence. We make the till here from a policy pi and the environment. And to evaluate a state, so the state value of a state S, we just keep track of the rewards we receive from that state onwards. And a very simple algorithm that we can deduce from this, it's called first visit Monte Carlo policy evaluation. The general idea is that we just keep track of the states we visited in an episode, and if we visited a state in the episode, so if we visit the state in the episode more than once, we just ignore it. We visit the state, we increment the state visitation counter, which is something that we maintain across all episodes. We increment the total return that we got in this episode, in this sample episode, on the state onwards, which we actually can calculate because we experienced the whole episode. And then we can just say, okay, we estimate the state value by just taking the mean return. So the state value is actually equal to the total return we saw in the state times the number we visited the state, or times the number of episodes that we visited the state. And as actually the state visitation counter approaches infinity, our estimation of the state value function will also come close to the real state value function of S, depending on policy pi. Because this is just considering by the law of large numbers. So one thing to mention, maybe you will also think about this, or this is also a question that came to your mind, is how can we actually be sure that we see every state? So in the previous example, in here, we didn't actually see such a state. And if you carefully look at the example, the policy in this case, if we do not start in the state, we will not ever see the state at all, because there is no action that actually advertises us to actually approach the state. So the question arises: how can you actually be sure that you visit every state? And the answer is simple, although maybe not very satisfying, because we actually only evaluate a policy. And following a policy hence guarantees that we will see any state under this policy, which is not a problem. So if there is a state which is not being really wanted to be visited by a policy, we do not evaluate the state, but this is also okay, because it doesn't play any role in our towards our policy. While this is really not a problem for policy evaluation, it will be a problem to model-free control, and we will actually discuss this a lot in the next lecture, but also in a lecture about exploration strategies that we will talk later in the course. Also to mention, there is another version of this algorithm which is called every visit Monte Carlo policy evaluation. The basic difference is that while we only use the first visit state, so imagine that you have an agent that is running through a grid world, and it runs in the grid world through loops, so we actually see a state twice. And the question is, how do you proceed such information? Because the return for this same state in this episode is different within this episode. So the first visitation of the state will have a different return than the second visitation. And the question is, how do you actually solve this? In first visit Monte Carlo policy evaluation, you just consider the first one, and you just you just throw away the information about the return from the second one. In every visit Monte Carlo policy evaluation, you would just add also the second visitation to your statistics, and you will perform a computation a lot on that. The question, which one is better? It really depends on the domain. Which one is better? It really depends on your problem. However, in practice, you do not really need to take care about this, because actually also through visiting a state a lot more and oftentimes this actually averages out. Okay, so here a little pseudocode about first visit Monte Carlo prediction. So it's just working like this. You have an initialization, so we actually initialize the value function arbitrarily. Doesn't really matter how you initialize it, because you actually always absolutely assign new values to your value function. And you have a return list that is also empty in the beginning. And then the procedure is like simply as it gets. You like do a loop forever episode, which you also have seen in the dynamic programming examples. And then for each of your episodes, so you sample trajectories from the environment, meaning that you just throw the agent into your MDP and you let it just interact with the environment until the episode terminates. And you just save all the stage action reward sequence in a list, and then you loop through each state of the episode, but from the back. So you start not in the beginning where the agent started. You start at the back, and what this easily lets you derive is for each of these states that you encountered through the episode from the back, you could just calculate the return, which is basically the discounted return of the state you're coming from, like seeing from the back, plus the reward that you get transitioning from the state to the state you're actually coming from the back. So actually you're turning the state you're getting into, which is basically the return for this current state. And then the thing is, then you just consider the question, the state that you're actually now in there, if this state is somewhere in there too, so actually in the episode, actually have seen it earlier in the episode, then you just go to the next state. Or if it's not the case, you just append the return of this state to the returns of this state that you have seen also in other episodes. And if you did this, you added a new return to the return list of the state. You just update the value of this state, so the state value of the state, by taking the average over all the returns that you have seen for the state. Okay, so maybe let's make an example out of it so that you can actually see how you can use this in practice. So a simple example, well, not maybe very simple, but maybe so if you're playing blackjack in real world too, it might seem very intuitive for you. For all of you, I will also add a little bit of a notation and framework and rules to it. So let's actually define the game of blackjack as an MDP and actually solve blackjack or the value function of blackjack using Monte Carlo policy evaluation. So in blackjack, the general goal is to obtain cards such that the sum of your cards is as large as possible without exceeding 21. The game works as follows. So there is face cards like king, queen, and so on, and they count as 10. And ace counts either as 1 or 11, depending on what's best for you, actually. And the numerical cards count as the value actually suggests. Okay, so let's maybe formally describe how the state space looks like. So actually the state space is the current sum of your hand. We define the current sum of your hand to be between 12 and 21. Because we assume that if your sum is below 12, we just model an automatic twist, so you will actually never see a sum of cards that is below 12. What I did not say is that in the beginning, so you get 2 cards and also the dealer gets 2 cards. And one of the 2 cards that the dealer gets is shown to you. So this is actually the game. So while the dealer does not actually see doesn't see a card from you. So actually, okay. So you see, the state space consists of the current sum that you actually have on your hand. It's the dealer's showing card, something between ace and 10, and a number between 2 and 10. And the question is, do you have a usable ace? Yes or no? So is it actually counting as 11 or 1? Okay, so what actions can you actually do? So the game is fairly easy. You can either stick or you can either twist. Stick means you say, okay, I'm done. I will not receive any more cards. I'm done so far, which means that we let our MDP end. So actually, this is defined as the terminal state, so the episode will be terminated. Or we twist, meaning that we take another card. We will assume as a simplification in this case, that there is no replacement of cards. Okay, what is the reward function of our MDP basically? So if we stick, if we stop receiving cards, we evaluate our sum and the sum of the dealer cards, and if our sum is bigger, then we get a reward of +1. If it is 0, if we are having the same sum of numbers, and it's -1 if our sum is lower than that. And if we twist, actually we get a -1 result return if the reward if the sum of cards is larger than 21. So the episode terminates, and it's being 0 otherwise. So this actually assures that there is no point in time that we get a value larger than 21, and the episode didn't terminate so far. Okay, so in other words, if our cards exceed 21, we go bust, and then it's the dealer's turn. And if we stick, it's the dealer's turn, and if the dealer goes bust, we won actually. Okay. And now the question is, what's our policy? So actually, okay, now I defined everything. How do we play this game actually? How do we want to play this game? And we just use a simple policy which says we just stick if the sum of cards is either 20 or 21. And if this is not the case, we twist. So we always take cards as long as the sum of our cards is between 12 and 19. There's no discounting, so it doesn't matter. We just say it doesn't matter how long the episodes actually go, and the cards are dealt with replacement, meaning that counting cards is not really helpful. So, okay. So, how would you actually think? So maybe take a minute and think about maybe pause the video at this point and think about how could the value function actually look like as a function of the dealer's showing card and the player's sum. I don't know if you actually think or actually thought that it's like the case, but actually maybe if you now look at it, it like really seems like reasonable to you. What you see here is the value function or the winning probability in a sense as a function of the dealer's showing card and the sum of the players. And of course it's like we differentiate between if you have a usable ace or not, but let's just ignore this at this point. So if you do Monte Carlo policy evaluation to run actually episodes, and we do this a lot, and we use Monte Carlo policy evaluation to estimate the value function, after 10,000 episodes you will see something like this. So a very bumpy version of the value function in here with very much variance and noise in it. If you have no usable ace, it gets like very nicely aligned because there is like no so much variance in this because of the usable ace. And after 500,000 episodes of playing games, you actually see a very smooth value function, and I hope this value function also seems reasonable to you. But what it actually says that if your player's sum is like between 12 and 19, your value function is really low because there the probability is that the dealer actually has a larger value than that is considerable. But if you have a value of 20 or 21, this really becomes very this value becomes really, your value becomes fairly high. And what you also see is if the dealer is not showing an ace, and actually in order to have 21, having an ace is like an indication for this, you see that your value becomes really high, and if you have 20, the value becomes a little lower, and then it gets really down. And but what you also see is if the dealer has an A, if it shows an A or it shows a 10, there is a considerable chance that also the hand that the dealer plays is around 20 or 21, which actually would result in a reward of 0 or -1 for you, which is actually also represented in what you get over the averages of all the returns that you have seen so far. So now the question arises, now actually we know how blackjack works because we actually told you in the beginning, or actually we talked about this in the slide before. And the question is, why couldn't we actually use dynamic programming to compute the value function? And so this is not so. Maybe this is not so easy to compute. The question is, why is it not so easy to compute this? The thing is that we need a distribution of next states, which requires the environment dynamics as a tuple of pi. And why is this not easy to determine? And the question is, if you want to determine the probability transition between all these states, what you actually need is you would need to find a way to define the probability that you win. As a function, also you need to define the probability that you actually win the game as a function of the dealer's showing card. So what is the probability that you win and that you receive a reward of +1 when you have 14 on your hand and you choose to stick? What's the probability? While you surely can come up with a computation of that, and of course you can, so it's like everything is defined, you can analytically compute this probability. It might be easier to just generate samples through Monte Carlo, just run the policy and just evaluate how good you are. So it actually, in many cases, it's just easier to sample the environment and to generate samples and to estimate the average return instead of just calculating it. So this is actually something we really heavily rely on reinforcement learning a lot. So the general idea that sampling the environment is not only the only way to go, but it's in many cases, it's computationally cheaper actually to do this. In practice, this allows you really to get results quickly. Okay, so having seen how to evaluate policies using Monte Carlo, we can just like also compare it a little bit to what we did with policy evaluation in the policy iteration framework with dynamic programming, where we actually computed it using the Bellman equation update. If you remember, in dynamic programming where we did policy evaluation, we actually iteratively applied the Bellman expectation operation, which actually says that to actually get an update on this state, we actually calculate the expectation of all the next states and the rewards we get on this state on this transition, and this has actually iteratively been used throughout the whole search tree to update our state estimation value. And in Monte Carlo policy evaluation, it's quite different, because in Monte Carlo policy evaluation, an update on a value function is not along the depth of the tree, the width of the tree, but it's along the depth of the tree. So actually, in order to update a value of this state and this state, we just perform a trajectory, and this trajectory that we do through our search tree or our diagram is actually updating all these nodes inside here. So it's like a little bit like translated how we do our updates in the whole tree. Okay, so one more thing to mention is that in the previous example we just run episodes and sample the environment, and we just kept track about how often did we visit a state, and we kept track of a sequence. Actually, we maintained a list of returns for each of the states. So there was a list called returns of S, and actually what we want to do in practice, so actually this does not really scale well, because if we sample like a lot, like a million or trillion episodes from the environment, this would, however, this at some point would also exhaust the memory. So the general idea is, instead of actually maintaining explicit statistics of these nodes, what we here want to do, we want to just maintain an incremental mean of this sequence of state visitations. And what you see here is, so in the end, the state value is just the mean of all the returns we got on the state, and you can just reformulate how you calculate such a mean. So in this case, the mean of the state value is just 1 times the visitation counter, 1 over the visitation counter, and the sum of all the returns we got into there. So this is actually what we did if we average them. And what you can do is, you do not need actually to take to maintain the list of all the returns. It is sufficient to just store the current mean and the visitation counter. And if you have both of these, you just can update the new mean in terms of the old mean and the visitation counter. And this is just a reformulation by the end. You just say that you can just calculate the current mean, which is basically the old mean plus 1 over k and of times the current estimation or the current value minus the old mean. And so maybe you can also think of it like a little like a calculation of the old mean plus the new mean, and k is something like an error. So what you see here is an error term basically. So this is how is your old mean, how far is it away from the sample that you get, and you will add this to your old mean with a small weighting factor, and you can call this like something like a step size. And this is actually saying that what did you think happens and what actually happened, and you will update your mean a little bit in the direction of the difference. So this is the basic idea. Why do we talk about this? Because we will use this a lot also in the next lecture, where we talk about time difference learning, and we can like generalize this and saying that what do we actually want to do? We want to take care of our visit counter. So we need to we really need to track how often we visited such a state, and we will incrementally update our value function in order to reduce the error. And so this is just a reformulation. You can just do this. One thing to mention at this point is, maybe you do not want to really use the state visitation counter at this point, but you want to use something like value alpha, or something like what you also call a learning rate, which will somehow relax the original problem a little bit. It will not be the mean over the over all episodes that you get, but if you maintain some small value in here, you would like transfer this a little bit through towards a sliding window approach. So you really only take the samples into account, or the samples from episodes into account that are more recent. So you will forget what you have seen a really long time ago. Although this is really not equivalent to a sliding window, it's like something like a sliding window. This could be really helpful if something like your state transition probabilities change, which is basically called a non-stationary, which is basically called something like non-stationary dynamics, where the dynamics change a little bit. Like imagine a grid world where you have wind, and in an hour there's no wind at all. In this case, it might be very helpful to just forget what you have seen an hour ago, because this is not really helpful anymore. Okay, so this lets us derive our general update framework, which says, okay, our new estimate is our old estimate plus a small step size times our target minus our old estimate. So this is what we're doing here, and this is also what we will build upon in when we talk about time difference learning in the next video.